Good day. Thank you very much for inviting me to the UK Offshore Wind Day hosted by British Embassy Seoul. My name is Matt Smith. I'm the head of sales for ZX Lidars, and I've been working with them for coming up for 14 years. The topic we're looking at today is offshore wind. What can wind lidars do for you today and tomorrow? ZX Lidar's view of the benefits and value of wind lidars for offshore wind. Contents today are what is wind lidar, a short history of lidar offshore, floating lidars as of today, where else do you find lidars being used, and floating wind today and tomorrow. So we're starting with what is wind lidar. This is the basic principle of wind lidar. This is a description based on the continuous wave lidar approach rather than pulse lidar, but essentially they're the same thing. Aerosols are being carried along in the fluid that is the wind, and therefore being carried at the same speed as the wind. The laser radiation scatters from aerosols, and we can see this here where the emitted beam is also being reflected back down the same path. This gives us the line of sight wind speed components from the induced Doppler shift. To go into some more detail, ground-based continuous wave wind lidars use a Class 1 eye-safe infrared beam of coherent radiation to illuminate natural aerosols in the atmosphere hundreds of meters above their installed location, and are precisely focused at user-configurable ranges down to ground level, covering the complete wind shear profile of relevance to a modern wind turbine and its potential performance once constructed and in operation. A small fraction of light is backscattered into a receiver within the LiDAR, and motion of the target particles along the beam direction leads to a change in the light's frequency through the Doppler effect. This frequency shift is accurately measured by mixing the return signal with a portion of the original beam and sensing the resulting beats at the different frequency on a photodetector. Since a single LiDAR measurement only provides the component of wind speed along the beam direction, known as the line of sight or radial velocity, it is necessary to interrogate the wind field from a number of different angles by scanning the beam to allow the full 3D wind vector to be reconstructed. A modern conical scan pattern rotates the beam, intercepting the wind at different angles, thereby building up a series of 50 measurements every second around a disk of air from which the wind speed vector can be derived. This high-density measurement approach offers the ability to apply a variety of post-processing techniques to extract further benefit from the LiDAR data in applications such as measurements offshore on floating platforms. And this is represented on the image on the right here, where we can see the different heights being represented by different colors, and the strength of the Doppler shift being represented by these arrows, strongest in the upwind and the downwind directions. So continuous wave LiDARs focus all of the available laser power at the measurement height of interest, and this means that we're able to achieve maximum availability independent of range in any environmental condition where there may be fewer particles to provide backscatter from. These clean air environments are often found at high altitudes or during winter on large land masses, not typically found offshore. It allows a lower power laser to be utilized within the continuous wave LiDAR design, and it's enhanced by the scanning of the beam and no need to stop and stare, which you can see with other LiDAR technologies. This offers a true Class 1 eye-safe laser. Now, the CW LiDARs sample up to 50 measurement points every 1 second from the measurement height of interest, and these 20 millisecond samples allow for accurate application of CFD conversion when operating in complex terrain, fully utilizing all 50 measurement points within the CFD processing. Up to 90 degrees of the scan can be blocked by fixed objects without impacting accuracy. Further, the CW LiDAR can be deployed within fixed structures such as lattice towers of masts. And there's an immunity to orientation of positioning. Simply deploy the LiDAR, you align it to north, or you record the orientation offset and input. And when on a dynamic thing such as a buoy, that can actually be input live. So looking at the history of LiDAR offshore. The first offshore LiDAR certification measurement occurred in 2006, and you can see that in the top image. That's the Pheno 1 platform with GL, Gamantia Lloyd, including performance verification against the mast. The first floating LiDAR trials are in 2009, and it's very difficult to see it, but you can see in the foreground the grill of the 150 original model lidars, and just in the background there you can see a little spar buoy which also has a lidar on it. And that was off the coast of Norway, just doing a proof of concept really. And then essentially we start long-term validations of fixed lidar with masts offshore. The picture at the bottom here is actually that example where the lidar is deployed within the lattice of the mast, and it was over 4 years in the Netherlands. And there were also things like North Wind going on at the time, which was looking at all the different masts, adding in some lidars, actually adding in some sodars to try and provide a wind atlas for the North Sea using traditional and new methods. And this started culminating in the realization that lidar had something to offer in the offshore environment. The need for lidars was apparent on two fronts. The need to measure higher, the masts weren't getting to current hub height, never mind future turbine models hub heights, and the costs for fixed foundation met masts were about 12 million British pounds, and the site's water depths were getting deeper. And we also could identify that this would provide no solution as we went into any kind of floating offshore wind market. The history of floating lidars, well, literally, I think I've shown this diagram before here. We won't argue about Axis and CZEFA who went first and such like, but you can see that back in 2009 we were seeing the introduction of commercial offerings within this space. And essentially, after the demonstrators, innovators, and early adopters, it was clear that the wind industry wanted LiDAR measurements. The value was there, the heights being measured were useful. Carbon Trust's Offshore Wind Accelerator is a collection of offshore developers, and they paid to explore floating LiDArs and to build a roadmap to be able to use them commercially. And this typically started off with putting these floating LiDArs next to traditional mast structures, as there were quite a few still about at the time. This evolved and it became the default standard for the development and use of LiDARs. And since then, the OWA has issued an update to the roadmap, as well as an IEA guide has been issued to procuring floating LiDARs. But this is still evolving. And essentially now the IEC has a standard in development, looking at the deployment, documentation, uncertainty, verification, and wind resource assessment. And it's important to note here at the moment is that the technology is actually evolving and maturing. The confidence is there. And actually everything is about the LiDAR at the moment, but technically it is just a sensor on a buoy. So why continuous wave LiDAR for floating LiDAR devices, FLDs? So the Fraunhofer Institute for Wind Energy Systems simulated motion-induced measurement errors for wind measurements using LiDAR on floating platforms, and it considered various simulations, overall concluding that continuous wave LiDAR is less susceptible to motion-induced errors when compared to pulsed. Equally, natural power looked at the average effect of a periodic sinusoidal tilt motion, and it reduces the error by a factor of approximately 2 relative to the static case. For the cases of static and low frequency periodic tilt, vertical wind speed has no effect except at very high tilt angles. And it also concluded that for tilt less than 5 degrees, bias is seen as 0.25% or less. Now, bear in mind this is about the individual measurement, and what it didn't necessarily consider is the fact that the industry is using. There was the obvious benefits of continuous wave LiDARs, lower susceptibility to motion-induced errors, but essentially, the industry was looking at 10-minute average data, which allowed it to have as many times as you were on the left-hand side of a wave, that was balanced out by the right-hand side of a wave. And that actually allowed for very strong correlations with non-moving references that didn't require motion compensation for the moving LiDAR. On top of that, there are also practical considerations. With an extensive track record on fixed offshore deployments, there are some practical benefits to the ZX LiDARs. A sloped window practically helps keep the window clean. Simple screen wash and durable silicon wiper, which is a continuous LiDAR benefit, as we don't need to have necessarily as clean a window to emit our signal through. And track record, very simply, ZX LiDARs were delivering a reliable measurement across several fixed platforms, and the confidence this builds offshore allows for a snowball effect. Essentially, people wanted to use something that had been proven to work reliably offshore. And you can just see on this slide here from 2010 a little bit of those early examples of that track record where we are deployed on Horns Rev, Talisman Energy, Beatrice platform, the Pheno 1 validation. We were identified as the sole form of measurement for the Nycoon project in British Columbia, and there are several other bits of work going on at the same time. And there was this fundamental confidence in the technology at this point. Looking at floating lidars as of today, literally just some images to show the current leading companies, I guess, in this space. We saw them on the Offshore Wind Accelerator roadmap as they join in. People like Axis and Fugro have been around since the very beginning of floating LiDAR offerings. And then we've seen things like Aeolus and RPS being designed specifically as floating LiDArs, whereas the Fugro and the Axis had Metocean businesses before then. Aeolus and RPS have brought in specific products, designed these specifically, all around the ZX300, and have been building up a good market and an international presence on this basis. Here, Fraunhofer are a commercial operation within a research institute, and they continue to offer floating LiDAR device services as well as continuing their research. And Titan, who have worked with Fraunhofer before, look to use the design and commercialize this for the Chinese market, but we've already seen Titan deployments in Korean waters. And interestingly, two of the Titan management team split off. Same management, they're also technical people, and created Blue Aspirations. Again, principally to compete in China, but essentially we are already beginning to see them consider further afield. Happy to talk about today is the fact that the expertise that exists within Korea has been developing its own floating LiDAR solutions. And on the left here, we have the Webon's floating LiDAR device. But I can remember talking with the Korean Institute of Energy Research as we delivered the original LiDAR and the prototype. The last time I talked at an event like this, we were showing their prototype version of this floating LiDAR solution. And equally, CTEC, with an experience with the Nomad hull, have been very successful in integrating a ZX LiDAR into that. And these two products are Korean homegrown products and absolutely exemplary for it. What's the world look like now? We don't see platforms being installed very often. They have a LiDAR on if they do. The measurement heights are still prohibitive from the mast anemometry point of view. We've seen numerous floating LiDAR-only projects built and operating. And the easiest examples are the Netherlands offshore wind farms because everything about those are in the public domain. The flexibility allows for more measurement locations on site, and essentially with the cost benefit as well, that larger sites, it's worth knowing any kind of flow variation around that site and essentially not picking up any uncertainties due to the fact that the furthest turbine is a mile away from the measurement location. The LiDAR data can be used for so much more. On a recent offshore wind construction site, there were 8 ZX LiDARs, some on buoys, some on the jack-up vessels, some on the offshore substations, some at the loadout port, and all of the data was made available to all involved for better planning and movement of resources and people, safer and more efficient lift planning at the port and at the turbine locations. Power curve tests with floating LiDARs, although that leads on to another topic, the cell-based LiDArs, but power curve tests have been conducted with floating LiDArs, and ZX LiDArs are estimated to be measuring on 95% of the offshore wind sites in development over the last 5 years. It really has been a privilege to be involved so extensively around the global offshore wind market. All of the floating LiDAR data used to date is looking at the 10-minute average wind speed and direction. And as we see more markets and sites becoming available, we are seeing a more varied wind regime, including turbulence, presenting offshore. This then links back to onshore and to the use of LiDAR turbulence measurements in general. There are several industry activities looking at how better to use LiDAR turbulence, as it is the same wind, it is the same turbulence that's being measured. The volume measurement versus a single point like a cup or a sonic has scatter in the correlation. However, some investigation of single point turbulence measurements show that there was a fair degree of scatter between two single point measurements on the same mast. Offshore wind needing TIs part of the catalyst for the industry to find ways of looking at LiDAR data and how to use it across several use cases. And I think it is the fact that within offshore wind, so many of the sites are presenting without the option of looking at a mast-based anemometry approach. And places like in North America, the North Americans have the Consortia for the Advancement of Remote Sensing, CFARS, and there's a link here. And there is also the DMVGL Joint Industry Project cataloging where things are today with LiDAR TI and how this can be used for more effectively going forwards. Where else do wind LiDARs get used? Well, the cell-based LiDARs. Early in the deployment of larger offshore wind farms, it was recognised that traditional offshore power curve tests weren't an option. Siemens, Ørsted, then called Dong, and the Technological University of Denmark, DTU, came together to work out how power curves could be delivered from offshore turbines. And this is going back to 2011, 2013. This work was then implemented to allow for cell-based LiDAR measurements for power curve tests as part of the formal turbine supply agreement. This was then repeated with different models, makes of turbines offshore, and to include ZX LiDARs. And this procedure predated the development of the IEC 61400-12-1 edition 2, which allowed for the formal use of ground-based LiDARs for formal power curve tests and introduced the rotor equivalent wind speed exploration of turbine power. There is a nacelle-based LiDAR power curve procedure in development in the IEC, and all offshore wind farms are using nacelle-based LiDAR power curve tests where they are occurring as part of the turbine supply agreement. There was no other option. This is what they had to do. Looking at nacelle-based LiDARs, I can't help but turn to my own technology again as the example. So we're looking at two types of measurement here. One, which is the 50 points around the scan for a single average view of wind conditions approaching the rotor. And then measurement type 2 is where we take pairs of points from either side that can be made at vertical heights, slices above the ground, addressing the need for accurate hub height measurements, plus or minus 1%, as we can then choose which of those left and right measurement points we use. And essentially by building up this, we get a rotor equivalent wind speed calculation. Both measurement types can be taken at a number of user-defined ranges upwind of the. Here is a little graphical representation of this. The actual red and yellow stuff you can see there is actually the signal returns that we're getting. The red line would be the ideal fit, and the green line is the fit that we're getting from these measurements. This actually allows us onshore to look at complex flow. Offshore, it allows us to see wakes. And again, we can see terrain effects as they present offshore as needed. Looking at the way that we then look at measurement type 2, and we're taking a series of 13 slices of a point on one side and a point on another, we're able to build up this complicated picture of the full wind shear and veer profile from all of the approaching wind. And we can adjust for any nod of the turbine to make sure that we're picking up the hub height measurement and then above and below that. Cell-based LiDARs are the same. The value of being able to see the full shear and veer profile of the approaching wind does offer a more thorough understanding of performance. The ZXTM, shown here on the right, has been on an underperforming wind turbine and instantly identified untypical flow conditions in the top third of the swept area. Nothing else on the market would have seen this. And as offshore wind farms change hands and ownerships, the margins typically get tighter, and every kilowatt hour and every month of extended life can become more significant. And that's why these measurements are becoming more important at the start and during operations. Also, what happens with turbine upgrades and boosts, as these can be based on specific site conditions. The cell-based LiDARs allow detection of these site conditions and also allows for a forensic exploration of whether they made a difference and whether they can be tailored to the specific deployments. Note the permanent placement on this picture on the right. On the latest generation of offshore wind turbines, the inclusion of LiDARs is becoming a standard option. I'll very quickly go through this and the importance of accurate wind shear measurements. Essentially, this was work conducted by Vestas, and it was looking at comparing what the Met mast would see versus the LiDAR in terms of shear. And essentially, down here we can see the red lines represent what the met mast saw, and these blue lines represent the rotor equivalent wind speed measurements conducted by the ZX lidars. And what you can see is the fact that the assumptions made from the mast could have really misrepresented what was actually occurring in those hub height to top tip area. Now, this was very interesting for Vestas, particularly something like this particular version here, where you can see the fact that the curve is coming back in terms of wind speeds. We're seeing a drop as we're getting higher with height there. They were conducting LiDAR load measurements for this turbine, and essentially this allowed them to see truly what was being exhibited to the turbine in floating wind today and tomorrow. Korea is at the forefront of large-scale floating wind, both in terms of sites, but also in looking at some of the commercial challenges associated with turbine supply in this area. This is only my opinion, but the floating wind industry seems to be focused a lot on port logistics at the moment. And there is a desire to see the levelized cost of energy comparable to fixed foundations. From what I've heard, most floating wind installations have been the combination of a floating foundation with a wind turbine attached, each separately certified. The warranty on a turbine on a floating foundation can be delayed until the tilt and accelerations have been verified in situ. Now, this represents a financial exposure. Yes, you can get finance, but without warranty and consequently without insurance, what kind of finance can it attract, and has it been minimized to a reasonable rate? And I think that's unlikely. In Korea, without telling you what you already know, South Korea is a perfect setup. With the marine engineering expertise, the marine production capabilities, the sites, ports and support for floating wind, local wind turbine manufacturing, and a stable economic environment for international and homegrown developments. This somewhat oversimplifies the range of expertise that can be used and linked up, but with Doosan, Hyundai Heavy Industries, and possibly Samsung looking to address this market locally and internationally, there is a chance to make a leading role in large-scale floating wind. For example, what if wind turbine and floating foundation were combined as a single unit that articulated its performance against the measurement tools that would be conducting the initial site wind measurements? Why articulate and certify products against measurements that simply aren't ever going to be conducted on most sites? Would that make the difference globally? This confidence could be built, and this would differentiate Korean offerings on the global stage by certifying and articulating performance of foundation and turbine together. Thank you for listening, and I sincerely wish I could be there today to actually meet with you, talk with you, explore some of these ideas, and I sincerely hope in the near future we get the opportunity to do this face to face. But we're managing to do this in these challenging times. We're still developing offshore wind farms, we're still developing and innovating in floating wind, and essentially is that this market is part of the recovery from this horrible pandemic situation. My special thanks to the people that have arranged today's event. My special thanks to you that are listening to this. And I say thanks and hope that we can actually repeat this UK offshore wind event with the support of the British Embassy here in Seoul in the future. And my contact details are here if anyone would like to get in touch about anything to discuss today. And I can go into remote control vessels, autonomous vessels, and how I think about the floating wind market further, but I think my time has run out. So thank you very much for listening. Thank you.